last talk, to tell us about list decoding of univariate multiplicity and cold read solvents.
It's good to be in person and giving the talk here. Thanks for the invite. I'll be speaking on some recent work with Rohan Goyal, who's an undergrad at the Chennai Mathematical Institute, and my colleagues and student at TIFR, Mrinal Kumar and Ashutosh Shankar. So the starting point for this work comes from the seminal results of list decoding up to capacity, the explicit list decoding up to capacity results, first of Guruswamy and Rudra in the context of FRS codes, and subsequently of Koparty and Guruswamy and Wang for univariate multiplicity codes. So let's just quickly recall what these results show. They show that for every constant rate and epsilon, there exists explicit families of FRS or univariate multiplicity codes that are efficiently list decodable all the way up to the maximum number of possible errors. That is basically 1 minus r minus epsilon fraction of errors. And these are beautiful algorithms which do this. So our focus is going to be how efficient can we make this efficient algorithms out here? Can we make them nearly linear? Can we make them linear time algorithms? That's good. Focus, and in some sense the answer, our main result is that yes, we can get nearly linear time versions of these algorithms. But actually, as stated here, it's unclear whether one can even expect nearly linear time, because the original algorithms of Guruswamy Rudra, Koparty, and Guruswamy Wang only promised polynomial size lists. They did list decoding, and I'll state all of these problems formally, but I just want to state the result first, and then we'll go into more. They only promise polynomial size lists. Now, the list size is super linear. There's no chance of having nearly linear time algorithm. So one could ask, is this question, does it even make sense? But thankfully, beautiful work actually showed that these algorithms can actually show that they are not just efficiently list decodable, but they actually have constant list sizes. This was shown in a beautiful work by Swastik, Noga, Shubhangi, and Mary. About 6 years ago. And so this sort of, at least now you can ask, they are constant size lists, so we can ask the question, do they exist nearly linear time? And our main result is basically, we can further modify these algorithms such that now we can actually get width that run in nearly linear time. In particular, they run in time order n polylog n.
Does it make sense to just ask for nearly linear time in the list size?
Huh?
Does it make sense to just ask for nearly linear time in the list size?
It does make sense, except that we don't know what the list size. We have, right now, we only know upper bounds on list size. So I could say it's linear in these suggested upper bounds. Even at the Johnson radius, for example, we don't know for these codes what's the exact list size. Yeah. So actually, so this sort of answers affirmatively. Yeah. Yes. So it's a randomized algorithm, but the randomness component is going to come from the KRSW result. Our algorithm is going to be fully deterministic. We're going to give a deterministic implementation of the first part, which will then leave which will output a affine subspace. And then from the affine subspace to get to the actual list is going to be randomized. This is a randomized pruning algorithm of KRSW. We're just going to use that. So if you can determinize that, our algorithm also gets deterministic. So a couple of things. This was actually posed as an open question in Swastik's beautiful survey on multiplicity codes. Actually, it's an excellent survey. Mrinal and I have sort of, the last 4 papers of ours on multiplicity codes have been just basically answering one open question after. There are several more out in that list. It's a beautiful survey. I would recommend all of you to look at it. And yeah. Okay. So that's result. I said it's going to be In fact, when Swastik wrote the survey, because KRSW was not yet there, he actually asked this question for up to just the Johnson radius, not even up to capacity. It was not known even up to Johnson radius if you could get nearly linear time algorithms. So we'll answer both the questions. Up to Johnson radius, we'll get nearly linear, as well all the way up to capacity. Nearly linear time algorithms. So that's going to be the question. So what I'll spend the next 10 minutes or so just state what these codes are. Just we did them in the boot camp, but I'll sort of formally state what these codes are, put them in the historical context, and then we'll, in the remaining sort of last 20 minutes of the talk or so, we'll go into what are the proof techniques. How do we manage to get such nearly linear time algorithms? Any questions on the statement of? Okay. So let's just put some quick next. Because the starting point of all these polynomial codes are what our favorite family of codes, Reed-Solomon codes. We're going to be working with some finite field F, some degree D parameter, some degree parameter. And S, which is some subset, some set of evaluation points. F, and the Reed-Solomon code word is basically you're given some polynomial F of degree at most D, and this is encoded as a set of evaluation points. So basically, you're going to give it as P alpha 1, P alpha 2, alpha m. I'm going to give it. It'll be convenient for me. This is a notation which sort of it will view this as P of x mod x minus alpha. When alpha is the same section, it'll be easier for me to define this because when I go to the multiplicity and FRS restrictions, this definition will be useful. And it's clear that the rate of these codes is d plus 1 over n. The distance follows from the degree mantra is 1 minus d over n. So these are actually MDS codes. And we have a rich history of decoding algorithms all the way up to the unique decoding radius, and then in the 60s and 70s, and then in the 90s up to the Johnson radius for these algorithms. So and all this history, we first had efficient algorithms that went all the way up to the unique decoding radius. Then we actually had nearly linear time implementations of these. The original algorithms like Peterson, Berlekamp, Macy were polynomial time algorithms that did unique decoding up to half the distance. And then there were implementations of particularly the Berlekamp-Macy algorithm, which ran in nearly linear time, which gave n polylog at time. So that was in the context of unique decoding. So you have this 0 to 1, that's the distance of the code. So that's the unique decoding radius. Up to that point, we had, there were fast implementations of the Berlekamp-Macy algorithm, which basically gave, for the unique decoding world, it gave you fast algorithms. Then, following work of Madhu and Venkat, we knew how to decode this all the way up to the Johnson radius, which is 1 minus square root 1 minus delta. And we had they gave us polynomial time algorithms to list decode all the way up to that point. So Sudan, Swami Sudan gave it. All the way up to the Johnson radius, and then this GS is from 98. And after 4 years later, Aleknovich gave an implementation of the Guruswami-Sudan algorithm, which ran in nearly linear time. So just like we had a fast implementation of Berlekamp-Macy, Aleknovich had to do some extra work in order to get. It was a nearly linear time implementation. Okay, so one hand, what we wanted to know if we can actually go beyond what happens beyond the Johnson radius. Yeah.
GS has a superlinear list size. Had it acknowledge.
So you have to be careful about this. So just below the GS has, so the list size by just the combinatorial bound for Johnson radius is anything 1 minus epsilon from the Johnson radius, the list size is constant. At the Johnson radius, the list size is possibly polynomial. So Aleknovich says anything below the Johnson radius, he'll get nearly linear time. He doesn't answer. Actually, so at the Johnson radius, I don't know if you get nearly linear time, and I don't even know. I would have liked to say his algorithm runs in linear in the list size, but I don't know what it could be that at the Johnson radius too, the list size is actually constant. It's just our current bounds give you some linear in n. So Aleknovich result, in some sense, Guruswami-Sudan result goes all the way up to the Johnson bound. Aleknovich says for any 1 minus epsilon of j delta, it will give you nearly linear time algorithms, and there we know that the list sizes are constant. And we will be working in that regime. Everywhere there will be an epsilon, will be off by epsilon from the final point, and hence we know that the list sizes are constant from previous results, and hence we can expect nearly linear time algorithms. So there was this quest for asking for explicit codes, possibly accompanied with efficient list decoding algorithm that were list decodable beyond the Johnson radius. And it was in this context Guruswami and Rudra actually rediscovered folded Reed-Solomon codes, which were introduced by Krachowski in 2002. They rediscovered it in the context of following works of Parvesh Wadi, the context of list decoding, and showed that actually they were list decodable all the way up to capacity. And then a few years later, Swastik and Venkat and Carol showed that actually some other codes, namely the univariate multiplicity codes, also have these properties. So everything I say today will actually be true both for FRS and univariate multiplicity, slightly partial to multiplicity. So I will focus my attention fully on multiplicity codes for the rest of this month, but everything I say holds good even for FRS codes. So what are multiplicity codes? So let's change this one. So multiplicity codes are sort of, it's just the fact that it's just going to be, they are called multiplicity because at every point, in addition to giving the evaluation, I'm also going to give derivatives up to a particular order. So we're going to work with univariate multiplicity codes.
Do you have other boards underneath or no?
Huh?
Whiteboards.
You will know why they are covered. One extra parameter, which is the multiplicity parameter. Setting is going to be similar, and what we will give is now p of x mod x minus alpha to the power s. That's what the alphabet is going. So it's the encoding is going to come from. So in the Reed-Solomon world, this was living in f to the n. In the multiplicity world, this will live in fs to the n. And by the way, this definition works over all fields. When I talk about derivatives, we have to be a little careful about what derivatives mean. Derivatives make sense only when the characteristic is large enough. And currently, all the efficient list decodable results are only known when the characteristic is large enough. So we will assume that the characteristic, in fact, is large enough. So this is the same as this quantity is equivalent to more or less giving p at alpha, the first derivative at alpha, the second derivative at alpha, and all the way up to the s minus 1th derivative. For small characteristic, you have to work with Hasse derivatives, but I'll completely hide that under the rug. Let's just assume it's regular derivatives for now. Anyhow, these results work only for large characteristics, so we can, without loss of generality, assume that we actually are given at each point the regular notion of derivatives.
With respect to S?
Huh? No, so the definition needs a large with respect to S, but the proof actually requires the characteristic to be larger than the degree parameter. We don't know. Yeah. So the definition, at least the way the definition will possibly that require S. Actually, if you go with the this definition doesn't require any restriction on the characteristic. But the current proofs of list decoding up to capacity D have a requirement. All proofs, all earlier proofs, including our proof, that they work only when the characteristic is 0 or larger than the degree of the underlying polynomial. So the rate and everything just changes by an extra factor S. These are also MDS codes. And I want to ask if these are list decodable up to, firstly, you can ask up to the Johnson radius. A slight modification of the Guruswamy-Sudhan algorithm will show you that they're actually list decodable efficiently all the way up to Johnson radius. Now you can ask, are these? And they are, in fact, efficiently list decodable all the way up to capacity. And what our main result will actually be these two statements. These are the exact statements. What we'll show is we'll show both list decoding up to capacity nearly linear time algorithms as well as efficient list decoding algorithms up to the Johnson radius. Yeah, so this is just a restatement of this. Basically, for every epsilon, we'll show that for a large enough multiplicity parameter and for degree D and all fields of characteristic larger than D, you do have that the corresponding multiplicity code is list decodable from all the way up to capacity in time, which is nearly linear in N. So it's N and a whole bunch of polylog factors.
Does your alphabet size goes up?
Hmm?
Does your alphabet size goes up?
The alphabet size is F to the S.
It's
So think of S as a constant. No, for all of these results, S is a constant. So it moves from F to log F to S log F, the alphabet size.
So it's constant, like depends on epsilon.
The constant is dependent on epsilon. So you tell me how close we want to capacity, and I'll tell you how large multiplicity parameter you want. For all multiplicity parameters larger than that, this is list decodable up to those many fraction of errors.
And what's the dependence?
What is?
What's the dependence on the epsilon?
So yes naught is 1 over epsilon square. Yeah.
So the final alphabet is like n to the 1 over epsilon square.
The final alphabet will be D to the
D is like n, like
D is like N, yeah. Yeah. And you get a similar result for up to the Johnson radius. But here we don't have, this works for, the only key difference between these two results is this works for all multiplicity parameters, not just from a large enough point. And it works for all fields of all characteristics. There's no characteristic. It works. Just like it, this is an extension of the Reed's of, in some sense, this is a strict generalized. Aleknovich proved this result for Reed-Solomon codes. It was a fast implementation of Guruswamy-Sudhan, and we get a fast implementation for every possible univariate code we get nearly linear. That's the questions.
Is the characteristic better than FRS codes? Depend, like you also need again at least D.
In FRS code, no. So by the way, I have stated it for multiplicity codes. So FRS codes, one thing, there's no, on the Johnson radius, there's absolutely no characteristic. For this one, it's not a dependence on the characteristic, doesn't play a role there. There, the order of this. So FRS codes, you evaluate it at alpha, gamma square alpha, where gamma is an element of sufficiently high order. The order has to be larger than D. That will play the role of characteristic. So it can work with low characteristic fields, but you need a you need an element with large multiplicative order in the FRS. Which is there. So in some sense, FRS are work in are list decodable in every field as long as you want to lay your hands on this gamma. These we currently don't know for every field. We only know it for large characteristic fields. In that sense, FRS is more general than multiplicity. What time did I start? And I have another 10 minutes more.
Ready? Like, no, like
15 minutes more? Huh?
Am I bad at math?
Oh, sorry, it started at 9:15. It's not 9. So good. Yeah. Okay. 25. Right. Okay. So what I will do right now, what I'll do is sort of give a sketch of the proof of this statement, how we're doing it. And the way we go about it, we actually look at the proof. There have been, for multiplicity codes, there are 2 proofs of this, one due to Swastik, another one due to Venkat and Carol. Venkat and Carol's approach is in fact further inspired by a linear algebraic approach suggested by Salil in his pseudo-randomness manuscript. They use that to get a very nice linear algebraic framework to solve both FRS and univariate multiplicity. What we will do is we will actually recall this linear algebraic framework of Guruswamy and Wang. Look at the steps. It will follow the same steps. And there'll be some steps which you solve huge linear systems. But because we are working with polynomials, they'll be solving linear systems and hence run in cubic or quadratic time. But because these are polynomials, we'll show that the underlying linear systems actually have very nice structure. And hence, you can apply FFT-like techniques to get nearly linear time algorithms.
Is that also what Aleknovich did?
Yeah, this is actually, I'll tell you. So this is all Aleknovich's approach also. So we'll come to it. We'll compare and contrast. So let's look at, so let's look at the sort of the linear algebraic framework of Guruswamy and Wang. So what's the question over here? So you're given some received word, that is basically you're given n points alpha 1, alpha 2, alpha n, and the purported derivatives, list of derivatives at these n points. And you want to find all polynomials f such that have good agreement on these n points. The number of agreements is large enough. For the rest of the proof, I'm not going to go in quantitative parameters. I'm just going to give a high level idea of what's going on. And since Sudan's algorithm for list decoding, broadly, all algorithms for list decoding have followed 2 main steps. The first step is sort of what's called the interpolation step. You get an algebraic explanation of the entire data. And then once you've got this algebraic explanation, you sort of extract the polynomials from this. How you actually implement this changes from algorithm to algorithm, but this is the broad step of Sudan's, Guruswamy Sudan, Koparty, Guruswamy Wang. All of them have this. All algebraic list decoding algorithms have the same structure. There's a step 1, which is this algebraic explanation or the interpolation step, and step 2, which is extracting the polynomials from this algebraic explanation. So let's state what is this in the context of univariate multiplicity codes as done by Guruswamy and Wang. The first step is basically you want to find some explanation. In this way, the explanation will be a polynomial of the type, it will be an m plus 2 variate polynomial. M is another parameter we are going to introduce into the system now. M is not, so S was the multiplicity parameter. M is typically, think of it as smaller than S. It's going to be 1 over epsilon. S will be something like 1 over epsilon square. M will be something like 1 over epsilon. We're going to come up with an algebraic explanation of the following type. It's an arbitrary polynomial in X, but linear in the Y variables. So it's going to be of the form AX plus summation I equals 0 to 1, 0 to m, yi bix. We're going to look at this explanation such that every f that has high agreement, that every f in the list will satisfy the following differential equation. There's a bunch of interpolation conditions. The interpolation conditions are tailor-made such that this is a consequence of it. I haven't written down the interpolation condition. They write a bunch of interpolation conditions so that now you take this polynomial q and plug into it f, the first derivative of f, all the way up to the mth derivative of f. These are all formal polynomials. When you plug them as formal polynomials, this formal polynomial actually vanishes. So in some sense, the interpolation conditions are tailor-made such that we'll see how this happens, but the interpolation conditions are basically a bunch of linear conditions to ensure that this happens for every f in the list. We'll come to that a little later. But these will be just, if you actually stare at them long enough, you can see that this will be just a bunch of linear equations. So solving this will be actually the standard way in how it's done is you actually solve a linear system, and that typically incurs cubic time or so. And the next step is now you're given Q. You know Q contains in its belly all the F in the list. You have to extract these F. So you want to now solve the differential equation. That is given Q, you want to find all F such that Q of F is 0. So you're given this differential equation and you want to solve it. If you stare at this closely also, you'll realize this is also a linear system, and you can solve this. And that's basically the entire algorithm of Guruswami and Wang. They will solve this. There's a linear system, a cubic time algorithm. This is another linear system, solve it. So you at this point, you get a basis. You can notice that the Fs that are solutions to this will actually form an affine subspace. The Fs that satisfy this form an affine. It's not hard to see this. They form an affine subspace. So the Guruswami-Wang approach will spit out a basis for this affine subspace. And it says all the close enough code words are in that affine subspace. And that was the end of the Guruswami-Wang algorithm. The subsequent observation by Koparty et al. Shows that you can, if it's contained in such a low dimensional affine subspace, you can actually prune it and show that the list size is even smaller. So at this point, they had shown that the affine subspace, they shown a affine subspace of dimension M. So Guruswami-Wang approach said that the list size is potentially possibly Q power M. And what these guys, what KRSW further, and so then they show that an affine subspace of, if you have an affine subspace which is just contained of code words which are considerably far from each other, any intersection of it with a ball can't contain more than 1 over epsilon to the power M code words. That's the statement which they prove. This is actually a subsequent this version of it is a subsequent improvement due to Tamu. But once this, you can, and they also showed that you not only hold this holds combinatorially, there's an algorithmic randomized procedure which, given the affine subspace in its basis, can actually exactly output this. So that's the sort of broad outline for the existing algorithms for list decoding of univariate multiplicity codes. And what we want to know is, we want to make each of these steps run in nearly linear time. Thankfully, this step is already nearly, once given the affine basis for the affine subspace, it's already linear. So step 3 is not going to be a concern. Step 1 and step 2 are going to be our concerns. We want to make both these steps run in nearly linear time.
So the first, what is this 1 over epsilon to the n? That's not a constant.
It's M. It's a constant.
M is 1 over.
M is itself 1 over epsilon.
Okay, m.
Yeah. Sorry, this is M. Yeah. Okay. So what we want to do is actually take these two steps, stare at them a bit closely, find out if actually these steps can be run in nearly linear time. Questions? So this, so far I've done basically a recall what Mary and I did in the boot camp.
M here is S in the previous board, right?
What?
M here is S in the previous board, I would say.
No. So M is more like 1 over epsilon. S is more like 1 over epsilon square. So M is another parameter that we will choose in the algorithmic, which will be large compared to epsilon, but small compared to S. Yeah.
Isn't the lower one then m to the power of m?
M is the constant.
M is a
Oh, okay. So,
Yeah.
so how is it better than m?
No, this is dimension M, therefore the list size is Q to the M. And Q is N. So at this point of time, the list size is N to the power 1 over epsilon. So here it becomes the list size is 1 over epsilon to the power 1 over epsilon. So it goes down, the list size goes from polynomial dependence on N to a constant on. Okay, so what we'll do is our broad outline will be the same thing. We'll have the interpolation step, we'll have the differential equation. By the way, even Aleknovich, going to Erit's question, Aleknovich had the same sort of issues over there. There was an interpolation step of, it was a different one. It was only bivariate. It was not an m plus 2 variate polynomial. The bivariate algebraic explanation, and then you had to factorize. And that, so by the way, so the recipe we will follow for this will be inspired by Aleknovich. But even for people who are familiar with Aleknovich, we'll give a slightly more straightforward proof of this step. This one, Aleknovich, notice that we had to do in Aleknovich's cases, we had to factorize. Particularly, you can ask whether we can do nearly linear time factoring. We still don't have an answer to this. The best factoring algorithms of bivariate polynomials run in n to the 1.5 time, not nearly linear. But notice we don't have to factorize. We want to only find solutions of the form y minus f. These are special kinds of factors. And Roth and Ruckenstein had shown that actually you can with this. So Aleknovich just uses a off-the-shelf product. Okay, this step, this is his main step, and this uses the shelf product, and that's how Aleknovich gets the fast implementation of Guruswami Sudan. Here we don't have fast solutions for him. We have to also go into this step and solve this in nearly linear time. Okay, so let's get to what is the step? What is the first step? So let's do each step one at a time. So let's take the first step. I want to find now a equation Q that captures the entire list. I want to find a polynomial Q of not too large a degree, so that every f in the list satisfies this differential equation. How do we go about doing this? So let's state what exactly happens here. So we want such a polynomial identity to be satisfied by when you plug in f. How does one ensure this? We ensure that at f, so basically this, to satisfy this, we say that for every point, for each, so this is step one details. So for each alpha n s, for each I in n, we want to ensure that we want to put some conditions on this one so that every f in the list satisfies this equation. So the way it's done is you ensure that alpha I is a root of some polynomial with large multiplicity. In fact, the polynomial which I want is exactly of Q of f with large multiplicity. That's the conditions you're going to with. In fact, multiplicity, the exact multiplicity condition is s minus m. We're going to set this. So we're going to ensure that we're going to write a bunch of linear equations that are going to do this. Notice a root is just stating one particular linear equation is 0. Stating that it's with multiplicity s minus m is going to state s minus m linear equations. We want each of these, we want s minus m linear equations to be 0. Notice that's s minus m linear equations just for one point alpha I, and there are n such points. So in some sense, so this thing is got sort of broadly inspired by Aleknovich. What we're trying to find is for a particular alpha, let L of alpha I be the set of polynomials that satisfy just for this particular this one. What we want to find is a Q in the intersection of all the LIs, because we want to find it for each of the LIs. Therefore, if it has large enough agreement, then you can say that this QF vanishes with has a very high order 0, and therefore it has to be identically 0. You want to ensure this. So Aleknovich's contribution was writing it this way meant that you had to do some operation here, and you had to take an intersection of these objects. Aleknovich calls these lattices. These are actually fx modules. These are, if Q is a polynomial of this type, multiplying it by a polynomial by in just x will still retain it in the solution. So these are fx modules. What we want to do is actually find an intersection of these modules. So working with an intersection module is this. The question is there an alternate description of this intersection module? And that's precisely what we'll show. We'll show that there is, in fact, a very nice alternate description. So let's look at this lattice instead. L is defined to be h of x product x minus alpha I to the power s minus m, I going from 1 to n, plus summation h and hi is an arbitrary polynomial. To define what this polynomial ai is some polynomial ai of x where ai satisfies the kth derivative of a at the point alpha j is actually beta j I plus k. Something to do with this one. Notice that this is basically I'm setting ai is a bunch of polynomials so that its derivatives have this. So Hermite interpolation will give you can lay your hands on the ai very fast. It's just interpolation. If it was just evaluation, this will be Lagrange interpolation, which we know how to do fast. This is with derivatives, you do Hermite interpolation and you can lay your hands on ai. So we get this one. Thing I want to claim is any such polynomial, so notice these polynomials are of this type, of these polynomials here. I want to first claim that any such polynomial actually has the property that if alpha I is a point of agreement, then actually it has multiplicity s minus m. The thing is set up such that for this to happen. Now I want to show that I can actually find a shortest non-zero vector polynomial in this fx module. So now I defined the module that I care for, and I want to find a small vector in this. How do we go about doing this? One way of doing this is, there are two ways to go about doing this. One is to show that this lattice is exactly this intersection lattice, and then use the Guruswami-Wang analysis, which uses dimension counting to show that there exists a short vector in the lattice, and then run some shortest vector problem in the lattice, which run extremely fast. So that's one way of doing it. We'll actually do a straightforward approach. We'll actually show that this lattice, we'll just stare at it right in the next few minutes. We'll stare at this long enough to show that this actually has a short. We'll use Minkowski's theorem to show that it has a short vector, and hence the shortest vector. When you run an SVP on these sort of fx modules, it will output a polynomial of not too large degree, which will be a candidate polynomial we'll use for this. Huh? No. This is, I don't use the fact that the characteristic is large. The characteristic is large is going to come in the solving the differential equation. Yeah. This will work for everything. There's nothing about the field that I use here. So let's.
You don't need to show there's always a solution. You just need to show that the desired f pops up as a solution.
No, it's easy to show. No, the fact that all the f's are what?
Any f that is close to the receiver.
Yeah.
That's all.
That is clear from the way I defined. So then no, but I don't know why does there exist a Q of low degree?
Because f is.
Huh? No, this Q contains all the f's. So how do I know when I put all the f's together, I will get an object of low degree? So there was this dimension counting argument that went on from, so then this one you have to show that the number of constraints is less than the number of variables to show that there's a non-zero solution.
You didn't show that any solution of this also satisfies step 2.
That we have this is done to ensure that so we will get that any alpha a will be a root of this, but to get to be equality, we need that the degree of this polynomial is low enough so that when I plug it in so many times, so I need the degree of q to have an upper bound on it. Otherwise, I cannot guarantee this. I need the degree of q, so I don't. So this showing q will satisfy that for every point of every input point, you do have it's as root, but it doesn't tell you that as a functional equation this is 0. If q had large degree, this will not be 0. So for that, you need to show that there is an existence of a q with low degree. So for this, what we'll
It's like Swastik's proof, but for the list-decoding algorithm, he takes all the endpoints and then he takes the variables and he just subtracts by the correct solution.
This is exactly the same thing. This is exactly the same thing, except done in the Guruswami-Wang approach, not in the y's are degree 1, not high degree. This is exactly the same thing. Yes.
The low degree part now is just the dimension counting.
The dimension counting, yeah. So to do the dimension counting, you'll have to show, there are two, right now I know two proofs of showing it. You have to show that this lattice and this intersection lattice are the same. This intersection lattice, Guruswami-Wang's analysis shows by dimension counting, it has a low degree thing, and hence we have it. But the only way I know how to show these two are equal is come up with a basis for the two lattices using Grobner basis and show that actually you can do it. So I'll give a more straightforward approach for this. So notice that I'm going to write every polynomial here. We can write it as a column vector. This is the coefficient of, this is the y-free part. This is the coefficient of y0, y1, and so on. So it's an m plus 2 dimensional column in which each entry is a polynomial in degree x. And this fx has this representation says there's a basis. Basically, there's a basis of x minus alpha s minus m and yi minus ax. This is a basis for this module. If you look at it, right, if I write these guys first, so this is what I'm writing is the degree of the polynomials of the basis in the x. I had to actually write the basis. What I've written is the degree of the polynomial. So this is the first base. This is the basis y0 minus a0. This is y0 minus a1, and I'm just writing the degree of the polynomial in x in the basis. What we can show is that the degree of the determinant of this is just going to be 1 plus 1 plus 1. It's going to be 1 into 1 into 1, so it's going to be s minus m. Minkowski's theorem will tell you there has to be a shortest vector of size. So there exists the shortest vector of degree less than s minus m by the dimension of the lattice, which is m plus 2, and that's sufficient for us. So we'll get such a thing, and sorry, I messed up something over here. There is an n. This is s minus m into n. That is s minus m to the n. Yeah, so these are the exact same calculations which happen with the dimension counting. So you all this. Notice this is a constant size. The polynomials here have large degree. They have degree up to n. But this is a constant dimensional lattice. It's an m plus 2 by m plus 2 lattice. So you can run shortest. So Aleknovich's observation is the fact that you can run shortest vectors on this lattice, find the exact shortest vector first in time, which is nearly linear in the maximum degree and polynomial in the dimension. So it's nearly linear in n, which is the degree of the matrix polynomials here, and the dimension of the matrix is m, so it's some polydependence on m, which is fine. We can afford polydependence on m. And that's basically the end of step 1. So step 1 is going to do this. It's going to solve this lattice problem, and we're done with it. And this is completely inspired by Aleknovich. Questions? Take another 5 minutes and wrap up step 2. Yeah. So step 2 is solving the differential equation. I want to solve, I've given Q of the form Q of x equals A of x plus, let's take a very simple case, Bx y0 plus Cx y1. Let's just take M to be 1, and I want to find all f's of low degree such that Ax plus Bx into Fx plus Cx into the first derivative of Fx is identically 0. This is what we want to solve. And I want to solve this in nearly linear time. Nearly linear time in the degree of f. The number of variables is constant, but the degree of f is possibly all the way d, and I want to solve it in nearly linear time with this. Let's ask first the simpler this one. How do I solve when, say, when I don't even have y1, something of the form ax plus f of x bx is identically 0. How do we solve such an equation? You divide and hope. So one way is f of x is minus ax by bx, and the hope is you can do this division fastly, and Chinese remainder theorem and all can be done fast, so we can do it. What I want to say is I don't want to do division because that's not the thing I can extend to the higher thing. So let's actually go into, open this up and see if I can do it. Let's see how to solve this efficiently. So let's, for the first thing, notice that B0, you can assume that the constant term in B, x doesn't divide both ax and bx, because then you can take out x. Then furthermore, you can assume that x doesn't divide bx, because if it divides this and does not divide this, there is no solution. So B0 is not 0. So once you have such a functional equation, you have an infinite set of equations going mod each x bar k. So I could write this, I could write each of these equations. I have, for every choice of k, I have such an equation. And then notice when I put k equals 1, I'll just get a0 plus fz. Let's assume f is of the form summation fi x bar I. I'll get f0 b0. So you can extract f0 from this. You write the next equation, it'll be linear in, you basically will get an upper triangular system, and you can solve this. That's what happens as a linear system. Yeah, that's a solution for this, but that's not a fast solution. It goes time run, you have to solve them. What you can further show is you can actually move from mod x bar k to mod x bar 2k in one step. That is, if I have a solution up to mod x bar k, then I can find the solution mod x bar 2k, and this is using ideas like FFT going into the picture. And what we will do is we'll show that this exact same thing will happen out for the differential equation. Huh? No. So FFT is just suggestion for the divide and conquer approach. There's nothing more similar to FFT than, yeah. So we'll basically do that. Don't have time to explain more things, but there's some more. You have to be a little careful, because in the case of this solution, there was a unique solution. Therefore, it's easy to do it. In our case, there's no unique solution to do this. So if you have a divide and conquer approach, if it says each time the solution possibly multiplies by 2, this will just blow up. You can't afford to do it. So what we will do is we'll actually not work with this differential equation. We'll show that if this differential equation has a solution, a related differential equation actually has a unique solution. Actually, it took us a while to realize this, and then we'll do the divide and conquer approach on the related differential equation. So that will solve it, and then from that we'll get back to the original. Basically, here we use the observation that the solution to this is an m-dimensional space. We know this. Therefore, for each basis, once you fix a basis element, you know. Let me stop at this. I can answer this one. We'll basically show a related differential equation has a unique solution, and then we exactly do this doubling trick. We'll get the solution mod x bar k From that, we'll go to mod x bar 2k and so on. And that's basically the whole idea. So both these will be run on nearly linear time. And we have to do this both in, we can do the same thing for FRS also and get nearly linear time implementations for all the list decoding algorithms that you are familiar with.
So the uniqueness is by fixing the initial conditions.
In fixing the initial condition. We have to get a basis. So we'll go for each of the choice 1, 0, 0, 0, 1, 0, 0. We're going to get a basis. So the initial condition, if you recall, Kursamy Wang's or this one, if you set the first few coefficients, after that it is unique. So we'll, for every possible one of them, we are going to get a basis for it. So we'll take a basis for this for x. If the initial conditions are just x bar I, for I being from 0 to m, we'll ask what's the extension. There'll be only a unique extension. Find that. Now we have a basis for the solution space. Then run the pruning algorithm over it.
But then this won't be near linear.
Why?
Because you're trying all initial conditions.
No, the initial conditions are only for a basis. For x bar I going from 1 to m. I'm going to just get a. So I will find all f's of the form x bar I plus some f x bar m. They will be, every solution will, once I fix that the first part is only this, it will be unique. So I'll find this out and then do it. Yeah. Sorry if that was fast. No, let's see, past time. Let's stop with this.
Given the time, maybe we can take questions offline, but let's take a 20-minute break and be back at